Hello everyone, welcome to the channel. My name is Neeraj Pratap Hazarika, and in this video we're going to talk about the coin change problem, which is a popular dynamic programming problem and has came in many companies interview questions like Amazon, Microsoft, Samsung, etc. If you are just here for the code, then I will give the code links of different approaches that I will talk about in this video in the description, so you can check that out. And it will only be in C++. So I will be discussing four different approaches to this problem. First will be the recursive approach without the use of DP. Then we'll talk about the top-down DP approach, also known as memoization. Then bottom-up DP, called tabulation. And the fourth will be a variation of the bottom-up DP. Variation of bottom-up DP. So uh, now let's first understand the problem. What he is saying. So this is the problem, coin change problem on Geeks for Geeks. Uh, so it says that given a value n, find the number of ways to make change for n cents if we have infinite supply of each s1, s2, sm value coins. So now let's go move on to my other screen where I will explain the problem. Okay. So the coin is saying that we are given an array which has different valued coins like 1, 3, 5, for example, and we are also told that we have infinite supply of each. So this has infinite supply, this has infinite, this has infinite supply, and we need to find such a combination of these infinite supplies of coins such that our sum is equal to the value n, and could be whatever. Let's suppose it's 7. So for 7, how many different combinations do we have? I mean, let's suppose we can just take the first coin to 7 times 1, 1, 1, 1, 1, 7 times. That's one approach. Second would be we can take, I don't know, 1 plus 1, 4. We'll make 4 with the help of 1, then just use 3. Then just use 3. This is also 7. This is also 7. We can use 1 plus 1 for 2 and just add 1. I just add 5. 1 plus 1 and just add 5. This will also be equal to 7. So there will be many such small combinations. So the question here, so I suppose you have understood what we need to do. We need to find the combination, and that too maximum number of combinations we can make to find its sum equal to 7. Since it is infinite supply, we can take each coins multiple number of times. So, and also we can see that from the problem, either we, and also from the problem we can see that either we choose a coin, or yes, or we don't choose a coin. Suppose we chose 1 here, we chose 1. Then we are again given option that from these 3 coins we can choose 1 again or not. Yes, we can. Yes, we can keep choosing yes, 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 yes. until the answer is 7. So it's kind of like a knapsack, the knapsack problem, where we need to choose either yes or no, and it is also infinite or unlimited, infinite or unlimited supply. So if we choose a coin, then it's not like we can't choose a coin again. So we can choose it again. So that's why it is unlimited and infinite and knapsack. Unlimited slash infinite and knapsack. So we understood these two things from the problem. Now let's identify how we can do it recursively. Then we'll try to identify if we can optimize that recursion with the help of the. So let's try to understand the recursive approach first. For this test case, 135. We will try to figure out the recursion. How is it happening? So we need to target a 7. So for 1, either we take 1 or we don't take 1. If we take 1, we took 1. Then uh, but our target is 7, so we are still left with 6 more to take. Oh, so we took suppose another one. Yes. One plus 1 still not equal to 7 yet, because still more 5 we have to take. So we have to take the combination, keep taking different combinations until this uh, we don't need to take any more. This x becomes 0. We don't need to take any more stuff. So this will go on until 7. Suppose if we consider we don't take 1, so we'll increase the consideration for this case to 3, because we are not taking 1, so we'll take a different number. So we'll take 3 or not. Suppose this index is I equal to 0. For all these cases, I equal will remain 0. But for here, we increase the I plus plus. So now the I has came from here to here, and we are now considering 3. So take 3 or not. If yes, then we are taking 3. So here what we took, we did not took 1, but we took 3. Still it's not equal to 7. 4 left. So we'll keep going. For in these cases also, could not take 3. We could not take 1. Then our I will increase. Then we'll consider for 3. Consider for 3. So this is what is happening in the recursive tree. Yes and no. So if we can write this in one line, the entire recursive process. Suppose this is a function, and there are some inputs. I'll write it later. So what we need to return is if we is the sum of not take and take. So if we take, then it will go inside one recursive loop. If we don't take, it will go inside another recursive loop. The sum of this recursive loop where we reach this x equal to 0, that we want. So that's why, suppose this function of not take, of let's say take, yes, and this will be the function of not take. No, we'll write this later. And when will we end? When our x will become 0, or we have reached all this sums has become 0. So sum equal to 7. Then we'll return 1, because we were returning 1 because we have found a combination. This is not the proper way to of the actual code, but for explanation purpose, this is the high level overview. Now we'll write the actual code. We'll define the input, then we will put this input. Then it will all make sense. So function, in the function, the quantity will come. Let's take this quantity. Okay. Now here will be int and here will be brackets. Array. Let's leave 3 for array. I'm writing this. Then our target value will come. Before target array, let's input the size also. Let's suppose size of the array is m, or let's write size. Size to be easier to understand. Size, and so I suppose this is the target. This is the target. And that's about it. We need the coin array, the size, and the target. Now our the return function is similar to here. Function of yes and function of no. So if we suppose we uh, consider we'll consider from the right here, because since recursive approach is the top-down approach, so we need to consider from the n case, and because we consider from the n case, it will call in the smaller subproblems from this n case. So suppose we here as a coin array, same coin array, and our size will be, it's the coin array, and we took it. So size will be the same, because here size is equivalent to the I that we took. Here this I we are taking, we are starting from the end. I equal to size minus 1, obviously. Size minus 1. So when we took the size, when we take this in consideration, we're starting from we are doing from the end, because this should be the final answer that should be returned for the whole 1 2 3 4 5. We want the answer, right? But to find the answer to 1, 2, 3, 4, 5 entirely, we need to find answers for the subproblems. Like for 1, 2, 3, 4, 5, the sum will be the final answer will be the sum of 1 to 3, the subproblem 1 to 3, and the subproblem of 5 itself. The combination of both two will be our final answer. Like suppose we only took one array with only coin one. This one, or array with coin one, and our target is 7. Same, I guess same. Then it will be only 1 plus 1 plus 1 plus 1 on that. Then suppose we took a target of 1 comma 3. We coin array of 1 comma 3 and target is same. So here also 1 plus 1 will be there, and a new answers will also pop up, like 1 plus 1 plus 4 times, then 3. So you can see that for 1 3, 1 3 is array final answer. This 1 1 is common. So the array of 1 3 depends on the shorter array 1 and also shorter array 3. But for the so that's why uh, in this recursive approach we start from the n and we call upon the function again and again until it goes to the base case. Like if we have reached the size equal to 0, then that will be the base case. So for each case, it's recursive call. When we take a function, take a coin, then the target will decrease because we have to took suppose 5, then the target was 7. Now it will become 7 minus 5. Our target has decreased. For the next recursive call, now we have already took 5. Now we need 2 more to make it 7. So this is the x here. We need to keep on going until this is 0. If it is 0, then we found the correct combinations of coins. If it is not 0, like less than 0, then we have exceeded our target. And if it is greater than 0, then we can still take more coins. So that's why this target will become target minus the coin array size minus 1. Since it is 0 based indexing, so we need to do minus 1. This is for yes, if we took a coin. Now let's suppose if we don't take a coin. Let me write it here. Okay, this is in the same line. I don't think I can scroll. Yeah, I can scroll to write it more. So I'll write it here. If we don't take a coin array will be the same. You're passing the coin array again and again so that the array is available for the next recursive calls. And this is the function definition, so we need to pass it. The coin array will be same, but now the size will change. Since we are not taking not taking the coin of size minus 1, that is 1, 2, 3, 4, 5. size minus 1 will be this. Since we are not taking this, so then we will be taking something else, that is size minus 1. Size minus 1 1 minus 1 minus 1. We don't, for here, since we decrease this as size minus 1 here itself, uh, so in this function we'll just no need to put size minus 1 minus 1, since for calling we will do that minus 1 in the next recursive call of yes. So size minus 1 here, and we did not take anything, so the target will not change. The target is still 7. Target is same. So like let's consider for 5 the target was 7, and this is the array 1 3 5. The size is 3 and the target is 7. So for yes, our array is still 1 3 5, and our size is still 3, but our target has decreased because we have took the 5th coin. So our target has decreased to 2. 7 minus 5 2. But for here, since we did not take, our array is still 5, but the size has decreased to 2, and our target is still 7. Since our size has decreased to 2, the array is same, but we will only but we are considering that our array is still only 1 and 3. So our consideration, so actually our array is only 1 and 3. We won't consider 5 anymore. So this will be a sub problem. This sub problem also contributes to the final answer, because in 135 the combinations that we will find out will include the combinations of 1 3 also. So this will keep on going, but when will it stop? Yes, no, yes, no, yes, no. We will stop if we found our target. We found the right combination and our target has become 0. Makes sense, right? Target has become 0. Or we'll stop until this has become 0. N equal to the size. Size, that means our array has no more elements. Size is 0. And 0 minus 1 minus 1 element we don't have. And so these are two conditions. And also if our target is less than 0, then we'll also stop. We can exceed our target, right? If we take 5 2 times, here only we will exceed. 5 plus 5 is 10. It has. So we'll stop also at when target is less than 0. But for here we'll return 0 because we did not find the right combination. Here we'll return 1 because we found the right combination. So we found one right combination. This will add up with the final return. Uh, and for size equal to 0, that means we have reached the 0 mark, but we did not find, we are out of any consideration of points, but we did not find any right combination, so we'll return 0. Now let's write the base case in the function. So for size equal to 0, we are returning 0 because we have consideration of points. And for also, when we will return 0 is if our target has become target less than 0, we exceeded our exceeded the target. So that's not the right combination. We no point of taking or not taking anyone. We will return 0. But if we have reached the target equal to 0, then we'll return 1. Now let's code this in the GFG platform. We'll get time limit exceeded because for large test cases, we'll keep on calling the same functions, same sub problems again and again. See from here also. See for here. Yeah, if we take yes, then it will exceed. But if we take no, then again it will become like 1 3, and it will be 3 2. So although the target is different, but we will face many such occurrences where the target will be same and the array will be same. So in this recursive call, we'll find the answer. So again, we don't need to find the answer for the same set of input because we already know it. So there we need to use TP to optimize. Okay, now let's move on to GeeksforGeeks platform. Now let's code it out, the recursive approach. So you can see here that our size equivalent is M here, and our target equivalent is N here. Let's take the base conditions. The first base condition was if our size or N equal to 0, or for target or N has become less than 0, then we return 0. And to return 1, I did this part, okay. I'm gonna repeat again. Okay, let's code it out. Here they're given as, that is the coiner. Let's change it to coinary. And let's change this to size. Let's change this to target. So our base condition will be to for returning 0. When size is equal to 0, that means no more coins left for taking in consideration. And the second will be when target has become less than 0, that means we have exceeded the target. So we won't find the right combination anymore, so we'll return 0. If the target is equal to 0, that means we found a perfect combination of points, so we'll return 1. And for the recursive call, we'll first, if we take the coin for the yes part, it will be same coin array, and if we take it, the size will be same. The target will be target minus coin array, coin array, coin array, size minus 1. Okay, plus the count for the not part, no part, not in the point part. Only the size will decrease, and the rest will be same. Size minus 1, and target will be same. This will give a theory because we have not optimized the solution. So it has given the right output for smaller test case. So although it is giving correct output, but if you submit, then for larger test cases, it will give raw theory. See, it is given theory. Okay, now let's move on to the next approach. That is the top-down approach. Let's talk about the second approach, the top-down approach or the memorize technique. Here it will be almost be same as the recursive approach that we just talked about, but in addition to that, we'll add a DP table to call upon those values which are already calculated. So in the GeeksforGeeks program, we will be needing another function because in the driver we cannot change the driver code function call. So that's why the code will differ a little bit for to submit in the GFG platform. But if we had written the driver code or the main code ourselves, then we can do it in one function itself without the use of any helper function. So this is the function that the recursive approach that we just submitted. So here itself we need to just make a few changes. We just need to throw in a DP table inside the input array. Suppose this is a DP DP 2D DP matrix. Rest will be same, but instead of returning just directly, I did this part where I'm having difficulties in erasing. So battery नहीं है क्या? Okay, instead of directly returning it, we'll just add it in our DP. DP will be equal to this will be m, this will be size minus 1, and this will be target. Okay, erase this part. Okay, and DP will be equal to size minus 1 and target. This will be equal to. Okay, I did this again. That's perfect. So instead of returning, we just need to input this to the dp table size -1, and this will be equal to target. And so we need to write a few things more. And we'll return this. There are few more things I need to explain before we can understand this. Okay, let's move on to that. So the DP table, let's talk about the DP table. That is the addition we're going to do. So in this column will be our target values, targets, and in this column will be our size or the array index, coin array index, coin array. Suppose it was 135. So it will be three rows. 1, 2, 3. This will be 0th index. This 1, this will be 3. So 0, 1, 2, 3. This is equivalent to the fifth element, or you can say coin array 2. Array 2. And this will be 3. This will be 1. These are the targets. What was our target was 7, right? So in the last column it will be 7. To start from 0. 1, 2, 3, 4, 5, 6. And this will be the columns. So this will be the TP table. And our final answer, or the required answer, will be in the last cell. That is our cell which has target 7 and cell which has all the combination like 1, 2, 3, 5. This cell does not represent only 5. This cell represents the whole combination, its entire combination. Combination of the coin denominations. So we will fill this DP from the last. That means we will not fill it in the last. We'll call the function for filling this last cell. We'll call the function. Say this line. We'll call the function to fill this one. So since it will start from the last cell itself. So then it will call the call itself. The function will call itself. Then we'll move on to its sub problems. Okay, so this size will be the same. Our target will decrease. So to find the answer to this, we'll go to 7 minus 5, that is 2. We'll move on to the cell. This first yes part, yes part function call. We'll move from this function call to inside this function also. It will go again. It will create another sub problem, like go again inside the same conditions again. Then this will call 2 minus 1. It will become 0. So this will return something which will be equivalent to this one, this sub problem, because it will go from here, since this is 2 and our area of consideration is 5. So 5 minus 2 minus 5 will be go towards the negative side. Our target will decrease to negative if we call this function again. here. So this will return as 0. This part will return 0, and for this part, well, size will be decreased by 1. So it will make this function call. It will try to fetch this value, size minus 1. This is the size part, size 1. So 2, it will go to 1, and target is same. So for here also, it will try to fetch values from its previous cells. That is from here or here. So similarly, it will keep calling until it returns from all the final base cases returns ones or zeros. Okay. Uh, we won't fill this DP table. We'll fill this DP table systematically from the beginning. In the next approach that I'll talk about, that is the bottom approach, where we fill from the beginning, not from the end. In this approach also, we fill from the beginning itself, but we start calling from the end. But from the bottom up approach, we don't call anything. We directly fill the DP table by making 2 for loops. We already know the entire thing, that how it should be filled, which conditions need to be set for the for filling the DP table. So according to the DP table, it will fill with the help of the if conditions. So that's the third approach. I'm not talking more about it now, and I'm not going to fill the DP table in this approach. So let's try to write a function. The count will be same. Okay, count will be same. Extra will be the DP table. Okay, I'm not writing it again. Rest will be same. Only thing, and the DP will be initialized with all values as -1 -1. So this is the array, it's columns. Everything will be -1 -1. That means there is no values in it. Okay, we have not calculated uh, the subproblem to that particular cell. So if we calculate it, that means if we have already found out that if we've already calculated that's the problem, that means the piece of I, J, or some target size -1, target means here this part is size, rows is size, and this is a target size -1 because it is zero based indexing. We start from 0, and our size will be 1 greater than the index. So it will be dp size -1 target not equal to -1. That means we have already found out that particular subproblem, so we don't need to get inside the recursive call again. We will directly return that particular cell, dp size -1, again same, I'm not writing it. I'll return it. Rest will be the same. And just here, suppose we did not say, if we found out it is not equal to minus, we'll return here and the function call will end here. But if it doesn't end here, then we'll return. So if this happens, this won't happen. Yeah, if this doesn't happen, then this will happen. That means we did not found anything. We did not calculate the subproblem, so we need to calculate it. So dp size minimum, the target. So we need to calculate it. We'll calculate with the count yes no part. I'm not writing it again. I hope you understood this part, and now let's code it, and we'll get a solution accepted. See, this is the same as the recursive approach. Only thing is are this part, and this part. These three extra things. We are using the help of TP. In the GFG platform, I will be using a helper function. The code will be the logic is same. I'm using a helper function because this count function. Okay, let me show you. This count function is in the driver code itself. So it's calling array m and n, and there is no dp here. So if we initialize the dp and send it over here, then we not need to use the helper function. But I will use a helper function because in lead code also uh, you will be it will be in the same format, and you will need to use an extra function to initialize the DP, one function to initialize the DP, and one for function for the recursive call. Let's try. Okay, no. See, yeah, edit current part. So this will be the same. Now let's use a helper function. Here we'll initialize the DB, and here will be we'll make the recursive call. That's in the format. The data type function return type same, and let's write the helper function. Here it will be the same as this. Okay, exactly same. So let's cut this part and put it here. Here let's initialize the DP. We can consider array long int. We can also consider a vector, but for the sake of your understanding that you don't know the deep vector array in initialization. Well, first let me show the vector array initialization. We can do it in one line. Vector long int vector long int that's the DP. This will be the rows, number of rows. Rows will be size, and the columns will be vector int. We'll fill the columns now. Vector long int it will be target plus one. Target plus one, since it will start from 0, 0, 1, 2, 3, 4, 5, 6, 7. So 1 to 7 it is 7, and for 0 we'll need another column, so it will be 8. For target 7 we need 8 columns, for target 9 we need 10 columns. So target plus 1, and we'll fill each column with minus 1. So we can initialize the vector with one line itself, but for if we use array, then we need to create for nested for loop, then equal dp ij equal to -1. We need to do we can also do that, but in vector you can with this vector line help we can do it in one line itself. Now let's move ahead with this only. I think you have understood it, so no need to make the array implementation. So we have initialized the DP to the matrix. Now we need to send it to the helper function. Let's send it to the helper function. These will be the same coin array. That's this is the function called. So we need to remove the data data type, and extra we need to add the DP. For here we need to initialize it. For initializing we'll use vector and %dp, because whenever we keep on sending the dp again and again to the recursive call, we don't want to send a copy of it. We want to send the actual dp. We want to send it the actual dp, so that in the recursive call also, after the recursive call ends, when we return the answers, the dp should have those sub problems calculation in the cells itself. If we send a copy, those sub problems that we calculate will be deleted. It will again become -1 because we send a copy of it. A new dp table will be created each time in the recursive calls. So if we send array, if we send the address as an address uh, called by reference, then it will make changes in the original dp. So as I've shown before, here we'll add a dp size minus 1, and dp the column will be target. Same is not equal to -1, and we return dp because we've already calculated the value of that particular cell. If not, we need to calculate that particular cell for that particular subproblem. So dp target equal to. Here the recursive call is helping helper. Recursive function call name is helper, not count. So call helper, and for each call we need to send a dp again and again. Okay, and here we need to return, because this is our final function that will be called in the main, and the final answer will be returned from here helper function. It will get that value, then we'll return it with from the count function. So you guys, so like I said, we have initialized the dp here and send it. We are making the recursive calls here. Now let's try to compile it if there are any errors. We have got the correct answer for the test case. Now let's submit. The problem successfully solved. Now let's move on to the third, that is the bottom-up approach. We won't make recursive calls. We'll directly fill the dp table from the first or the top left corner of the cell till the bottom right corner of the cell, and our answer will be the final cell or the bottom right corner cell. After filling the entire table, we'll just return the cell. Now I will discuss the third approach, that is the bottom-up approach or tabulation method. In this approach, we'll not use any recursion. We'll fill the DP table from the top left corner of the table, that is the matrix, to the bottom right corner of the matrix with nested for loop. Suppose let's take the example 1, 3, 5, and our target is 7. So in this array, in the 2D matrix that will form will be from 0 to 7 and for columns, and 0 to 3 for the rows. 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6. For this is a slight variation that I did from the last approach, where I did not consider the 0th row. But for here, to because for the ease of understanding and for intuitively, you will be able to figure out that why is this happening. We need a base case for the roads. That is 5. For the base case of uh, we have a base case for the columns, that is 0. When our target is 0, we'll return 1. Uh, so we have created a base case for rows also. When our coins are 5, that is we don't have any coins to take for consideration, then obviously if we don't have any coin, we can't uh, make any combinations to get our target. So this will return 0 except for 0, because for 0 we don't need any coins. This For 0 it will always be 1, since we don't need any coins to make 0. But for rest of the part, it will all be 0, since we don't have any coins to take for consideration, so our target will never be achieved. But for target equal to 0, it will always be 1. We can always don't not take anything. And for all these other rows from 1 to 3, it will be the coins that are in the coin array. This is a coin array. Zero, 1, 2. But for here it will start from 5, then 1 is equal to 3 is equal to 5. So let's make the columns properly. So now our the main line of code that we have done in the previous approach also, the return that we did, the recursive call, that is there was two part, that is no and yes part. So here also there will be no and yes part while filling the cells, except for the first row and the first column. uh, it will always be the same, that is 1 1 1 and 0 0 0 for all test cases. Since for phi it will be 0 except for 0 target, and for any other values that you take, any other coin array, it will always be 1. So now this out of the way, so we can say that if I equal to 0, that is the first row, but nn, but j should not be equal to 0, then the dpij will be 0. This is true for all test case combination or any test case. But for j equal to 0 for rest of the part, our dp, that is for the target equals 0, our dp value will be always be equal to 1. Now for the rest of the tables, we know we have two part, the yes and no part. This is yes plus no part. So for the yes part, what we did, recall, what we did in our last approach, that we uh, reduce the target minus coin array dot 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 I minus 1. So pausing. Let me correct myself. In the previous approach also, uh, we considered the similar DP. Our DP table was had m plus 1 rows and n plus 1 columns, that is size plus 1 rows and target plus 1 columns. So it is the same DP table, no change, no variation. But in this approach, I am telling you how we are actually filling the DP table. We for the yes and no part, that is from the cell I equal to 1, j equal to 1, our DP will fit in either of the two cases. That is, if there is a valid yes part, that is if our target minus coin array I minus 1, since we are we are doing and we are adding an extra element 5 for the rows of the TP table, and one is starting from here, that is 1. So I minus 1 will be coin array 0th index. So target minus 1, this means that we are considering this is the coin array 0 for one. For the I equal to 1 row, our coin array is I equal to 0, the 0th index uh, valued coin, and our target is the uh, row, the column that we're talking about. So this is actually J, the J that we are talking about. So if this is greater than equals 0, if this is valid, if there is a yes part, that means we have already calculated the value. So if there is a valid yes part, that is target minus coin array is greater than equal to 0, then we can add both the yes and no part. No part will be just the cell above it. So ij will be equal to dpi, the same row, and this is j minus coin array. I minus 1 plus dpi minus 1, the cell above it, and the same column. Else, make it else if over here, else if over here, else if else then else part, that means there is no yes part, no valid yes part, then we'll just copy the cell above it. See, if we look over here, uh, for the 1 and 1, this block, 1 block, uh, let's check if there is a valid yes part. That means yes, we can take the coin 1. So 1 minus 1 equal to 0. This is greater than equal to 0. That means there is a valid coin part which is already solved. So now we'll call upon this value. This is the yes part, and for the no part, I minus 1j, the cell above it 0. So the final value will be the sum of 2, that is 1. 1 plus 0 is 1. And for here also, 2 minus 1, that is 1. This means this block. 2 minus 1, 1 plus, and the cell above it. So here also 1 will be the value of the sum. If we really need to find a combination, then it will be obviously we are only given the one array, with only one valued coin. So to make two, we have 1 and 1. That's the only way we can make it. So that's why our answer is 1. For 3 also it will be the same. For 1, matter of fact, for 1, there's only one way to make anything, that is sum of all the ones till target. But from next row, that is we have 3 value coin. Now it will change. So minimum minimum we can make with only taking 3 is 3. Just if we take only 3, not if we don't take 1, only 3, then obviously if we take 3, then this our sum is equal to 3. So from here, j minus coin array will be valid. So 3 minus coin array I minus 1 is 3 minus 3. Here I is 2, so 2 minus 1, this 1, this is 1, 2 minus 1, so this is 3. So this will be valid only from here. So this part, the yes part won't be valid, and we'll copy the values above it. So 1 1 here, will directly copy it, the value, this code will run. But from here onwards, it will uh, copy the value of I minus j minus coin array, that is from here. The yes part will return 1, and the no part will return 1 also from the cell above it. So from here onwards, our coin array will be 2. So if we need to think about it, so we have now 1 and 3. We have both this to consider. For the third row, the fourth row, we have 1, 3, and 5 to consider. Entire stuff, entire thing will consider. So to make 3, and we have only 1 and 3 two options, there's only two cases, 3 and 1 1 1. So that's why our answer is 2, and no other combinations is possible. So similarly, let me fill the DP table. Here also it will be 4 minus 1 1, this will be 1, and this will be 1, so answer will be 2. 5 minus 3, this is 2, so this is 1, and this is 1, so this will be also 2. 6 minus 3, this is 3, so it will return from this cell. DP, we are calling, we are adding the value at DP 2 comma 3. That is this block. So this will, yes part will return 2, yes part contains 2, and the no part contains 1, the cell of it. So from here it will be 3, and this will also be 3. Now for 5, our yes part will start from here, 5 itself. If we take 5, then our answer, if we only take 5, then our target 5 can only be achieved. We can't achieve anything below 5 if we only take 5. So for all these blocks, it will be the cell above it. So 1 1 2 2. But for here, the fifth block will have, for the yes part, we have 1. This is 5 minus 5 equals 0. So it will return, yes part will have 1, and the cell above it will be 2. So 3. For 6 minus 5 1, yes part will return 1, and the cell above the no part will return 3. So this is 4. For 7 minus 5, that is 2. Yes part will return 1, and the no part will return 3. So our final answer will be 4. So that is how we are feeding the DP table. Now let's code it out in the GFG platform. So we will first create the DP table vector here. Number one. Then one more vector. Vector DP. Size plus 1 rows and target plus 1 columns. Size plus 1 and vector int. Each row will be filled by -1. So we'll have target plus 1 columns and will be filled by -1. This is the initialization of the table. Now let's fill the values. For I equal to 0, fill size I plus plus. For j equal to 0, equal to target plus target and j plus plus. For this is j. Now for the first row, if you can recall it, for the first row except the top left corner box, that is I equal to 0 and j not equal to 0, we'll fill them by 0. Since if we don't have any coins to consider, we don't have any valid combination with it. But for the column, 0th column, when our target is 0, then we always have one valid combination, that is not by not taking any coins. This is by not taking any combination. Let's consider it else here. So we don't need to write the last condition, and we can just put else in the last condition and add the value to the DP ij. So if there is a valid valid yes part, is point array I minus 1, j minus point array equal 1 is greater than equal to 0, then our DP will take the value of the yes part from the same row, j minus point array I minus 1, and will take part from the no part, that is the cell above it, I minus 1 j. And for the else part, where we don't have any valid yes part, and we can only take the cell above it, dpij will be equal to dp I minus 1 j. And in the end, our final answer will be available at the last bottom right corner of the DP table, that is DP size target. So let's see if there are any errors. Okay, int. I want to write int. Okay, with the correct value for the test case, sample test case, and problem successfully solved. I hope you understood the third approach. Now we'll be moving on to the fourth approach, that is the variation of the third approach, a variation of this approach. But instead of using a 2D matrix like we did here in this third approach, we will be using only a 1D matrix. See, we actually don't need so many rows. We can just overwrite the values in the same rows itself. I will show you how. Let's move on to the screen. Did this part okay when I'm just coding and saying nothing. Okay, for the fourth approach, uh, we'll talk about the variation of the third approach, variation of bottom of the box. But instead of using 2D matrix will use 1D matrix. You can say matrix 1D array. Or just say 1D array. And we'll only take the columns for this fourth approach. Suppose for the test case that we just considered 1, 3, 5 in the third approach, 1, 3, 5 and 7. So we can just make the 7 columns 0, 1, 2, 3, 4, 5, 6, 7. 0, 2, 3, 4, 5, 6, 7. For 5, we know that the first row in our third approach, which was our column was filled with ones and 1 in the first cell and then 0, 0, 0, 0, 0 in all other cells. So this is how we filled the first row in our previous approach. So we don't need multiple rows. Try to notice here. We can just override the values here itself. Like for I equal to 0 iteration, it will fill these values in the column. For I equal to 1 iteration, we can just take the sum of the previous values, sum sum I only suppose this is the array dpj plus equal to dp, so dpj plus equal to that, or else we can write, let me fully write it, dp equal to dpj plus dp j minus point array I I minus 1. Here also we will take two for loops, one for I and one for j, but instead of the 2D matrix that we consider, we will consider 1D matrix. It will consume some less space this time. So no part we took from the cell above. So this was suppose for here, this cell, the no part we will take from here, and the yes part we take from the same row. So here the no part is filled by the cell itself. Since we are overwriting the same row again and again, the no part is already present in that row. We just need to add the yes part like this. So will yes part can be filled with j minus pointer, right? I will check if it is valid. So if we keep filling on until the end, then our answer will be available at dp target. So, so I hope you understood. Let's move on to the GFG platform, where I will just make a few changes, then we'll have the code available to us. So here we don't need the rows, so remove the rows. Let's go to 2D matrix part, and for here, let's just fill it, target, +1, -1. And for the columns, I will remove the row part of each dpij. This part, rest will be same. The logic is same. And instead of here, it will be the dpj itself. dpj. And that fills the no part. And this row will remove itself. Now we can leave it. Yeah, we need to remove it since the dpj part is already present. Okay. Let's compile it and see if there are any errors. Oh, we need to remove this part too. We extra brings. Now let's run it. We got the right answer for the test case. Now let's submit it. Problem solved successfully. So with the slight variation, we reduce the space complexity as well. Thank you. I have explained the four different approaches that I mentioned. And if you feel there's anything else you want to add, then or you want to ask, then you can write in the comment section. I will also link some resources that I uh, read and viewed to help me understand this problem well. So, if in case you did not understand well, even after watching this video, you can refer to those resources.